A fundamental question in the field of cosmology appears to be approaching a turning point in our comprehension of the cosmos. For over 10 years, there have been two different types of measurements regarding the speed at which the universe is expanding. Observations of the current universe typically find that the rate of expansion, known as the Hubble constant, is about 9% faster than predictions based on early universe data. Researchers had hoped that James Webb, the most sophisticated telescope ever constructed, would help settle the matter once and for all, but consensus has not materialized thus far. Instead, the Supreme Observatory has cemented the discrepancy with remarkably precise new observations that threaten to upend the standard model of cosmology. The new physics required to adjust or even replace the 40-year-old theory is currently a subject of debate. Join us as we delve into how new ultra-deep photos from James Webb have verified that there is a severe problem with our understanding of the cosmos. It's an intriguing and interesting possibility that there is something we don't comprehend about the universe. The Big Bang erupted, bringing energy, mass, and space into existence in an instant. Then, the young cosmos was formed, an expanding, roiling plasma broth of matter and antimatter particles that popped into existence only to annihilate each other upon contact. Left to their own devices, this is how our universe began. Scientists believe that an unidentified imbalance allowed more matter than antimatter to be created in this plasma, preventing the cosmos from immediately destroying itself. Normally, the matter and antimatter inside this plasma should have eaten each other utterly. The plasma was crushed by gravity, a tiny portion of this matter was safely pulled from the fray as the universe inflated like a balloon due to the high energy density of its crowded contents, stretching space-time. Meanwhile, pockets were compressing and heating the matter, causing sound waves that were slightly faster than light to ripple across their surface. This is the standard story. It is believed that the first galaxies were connected by a vast cosmic web when ordinary matter, which interacts with light, congealed around clumps of invisible dark matter. Initially, the universe's content spread out, causing its energy density to decrease and the expansion rate to slow down. However, approximately 5 billion years ago, galaxies began to recede once more at an ever faster rate. This was caused by another invisible and mysterious entity known as dark energy. The most straightforward and widely accepted theory of dark energy is that it is an inflationary energy that is consistent everywhere and at all times, woven into the expanding fabric of space-time, and is known as the cosmological constant. In his general theory of relativity, Einstein gave it the name lambda. As the universe expanded, the overall matter density decreased while the dark energy density steadily stayed constant. This latter density was the primary factor in the universe's overall expansion. When combined with the energy densities of ordinary matter, the maximum speed limit of the universe's expansion is determined by dark matter, dark energy, and light energy. These are also essential components of the lambda-cold dark matter or LCDM model of cosmology, which charts the universe's expansion and foretells its demise, with matter eventually spreading so thin that it. Hubble Space Telescope on one of the Milky Way's closest neighbors, the Large Magellanic Cloud. Their result was explosive, an impossibly high expansion rate of 74 km per second per megaparsec when compared to the Planck measurement. However, Hubble lacked the necessary precision for the crowded regions of space the team was studying, causing some distant Cepheids to blur into neighboring stars. Dissenting cosmologists had some room left to argue that the result, however shocking, could have come from a measurement error. So when James Webb launched in December 2021, it was poised to either resolve the discrepancy or cement it. At 6.5 meters wide, Webb's mirror is almost 3 times the size of Hubble's, which is just 2.4 meters wide. Not only can James Webb detect objects 100 times fainter than Hubble can, but it is also far more sensitive in the infrared spectrum, enabling it to see in a broader range of wavelengths. By comparing Cepheids measured by James Webb in the galaxy NGC 4258 with bright-type Ia supernovas, another standard candle because they all burst with the same absolute luminosity in remote galaxies, after comparing several observations, including one by Friedman using the Hubble Space Telescope on the fast brightening of the most luminous tip of the red giant stars and another using light, Rees and his colleagues came to a roughly identical result, 73 km per second per megaparsec. A different result employing the bending of light similarly produced a value of 73 km per second per megaparsec. The results of the gravitational pull of big galaxies returned values of 69.6 and 66.6 kilometers per second per megaparsec. Cosmologists were left stunned. According to Ryan Keisler, a cosmologist at the University of California, Merced, who has been trying to explain the Hubble tension since the Cepheid distance ladder measurement is approaching 1% and the CMB temperature is measured at a precision level of 1%, a difference of 7 km per second, though not particularly large, is extremely unlikely to be the result of chance. An official attempt to resolve the issue at a 2019 conference at the Kavli Institute for Theoretical Physics, KITP, in California only caused more frustration. As the late Vera Rubin, who discovered evidence for dark matter, said at the time, there is something definite to explain. The new result left the answer wide open and split cosmology into factions chasing staggeringly different solutions. Their plaything after James Webb and another independent Hubble distance ladder result confirmed the Hubble tension. Cosmologists were left with three possible explanations in February 2023. This was because all of the involved parties undergoes a heat death known as the Big Freeze. Many of the model's predictions have been shown to be extremely accurate, but here's where the problems lie. Despite extensive research, astronomers are unable to define dark matter or dark energy. Ofer Lav, an astronomy professor at University College London and participant in galaxy surveys of dark energy, stated that most people believe that 5% of the universe is currently made up of ordinary atomic matter, 70% dark energy, and 25% cold dark matter. Observations have shown that the universe appears to be expanding at different rates, a discrepancy known as the Hubble tension. Methods that peer into the early universe show it expanding significantly faster than LCDM predicts. The embarrassing truth is that we don't understand the last two of them. But an even greater threat to the LCDM model has materialized. Thus, the only reason I can think of for them to disagree at this point is that the model we have between them may be missing something, because measuring the expansion of the universe requires a little bit more than a radar gun. According to Nobel Prize-winning physicist Adam Rees, who led the team that made the new James Webb measurement, the first method to measure this growth looks at the so-called cosmic microwave background, or CMB, a relic of the universe's first light produced just 380,000 years after the Big Bang. The imprint can be seen across the entire sky, and it was mapped to find a Hubble constant with less than 1% uncertainty by the European Space Agency's Planck satellite between 2009 and 2013. In this cosmic baby picture, the universe is almost entirely uniform, but hotter and colder patches where matter is more or less dense reveal where baryon acoustic oscillations made it clump as the universe exploded outward. This soap bubble structure ballooned into the cosmic web, a network of crisscrossing strands along whose intersections galaxies would be born. By studying these ripples with the Planck satellite, cosmologists inferred the amounts of regular matter and dark matter and a value for the cosmological constant or dark energy. Plugging these into the standard model spat out a constant of roughly 67 km per second per megaparsec. A megaparsec is 3.26 million light-years. Let's take a moment to reflect on this figure. A galaxy that is 1 megaparsec away from us will recede from us at a speed of 67 km per second. At 20 megaparsecs, this recession grows to 1,340 km per second and continues to grow exponentially from that point on. If a galaxy is more than 4,175 megaparsecs away, it will recede from us faster than the speed of light. A further technique to determine this expansion rate makes use of pulsing stars known as Cepheid variables, which are dying stars with outer layers made of helium gas that expand and contract as they absorb and release star radiation, causing them to regularly flash like far-off signal lamps. Astronomer Henrietta Swan Leavitt discovered in 1912 that a star's absolute brightness could be determined by measuring how slowly it flickered. This groundbreaking discovery allowed astronomers to measure a star's distance and turn Cepheids into plentiful standard candles. By connecting observations of pulsating Cepheids together, astronomers can create cosmic distance ladders, with each rung taking them back in time. This is one of the most accurate methods available to astronomers today for measuring distances. Wendy Friedman, an astrophysicist at the University of Chicago, said to build a distance ladder, astronomers construct the first rung by choosing nearby Cepheids and cross-checking their distance based on pulsating light to that found by geometry. The next rungs are added using Cepheid readings alone. Then, astronomers look at the distances of the stars and supernovas on each rung and compare how much their light has been redshifted, stretched out to longer, redder wavelengths as the universe expands. This gives a precise measurement of the Hubble constant. In 2019, the method was used by Rees and his collaborators, who trained the